Hello everyone, this is Dr. Young, and in this video we're going to continue talking about enthalpy, but we're going to start doing some calculations and figure out how much heat is transferred when you change phases, right? From solid to liquid, liquid to gas, solid to gas, etc. So remember that we were talking about the change in enthalpy before in some of those definitions, and we were saying, well, that the change in enthalpy is going to equal the change in the internal energy and the change in the PV work. But we're not going to see much PV work, we said. So we're saying that we can simplify our change in enthalpy is basically the same as our change in energy right now, especially because we're not talking about entropy or anything else, which is going to be the same as our heat transfer, right? So if I want to solve for the change in energy, how much heat is absorbed or released from a different process, you'll see all three of these terms being used, and I'll try to use these terms for you today. In this video, what we're going to do is we're going to focus on the phase changes, right? So we're going to have equations like this one here, where our heat, Q, is going to equal the grams times the heat of vaporization, the delta H of vaporization. So let's talk more about that. First, let's make sure we know our phase changes so that we have all of this in vocabulary here. And this is supposed to be, as I kind of used these diagrams before, this is supposed to be a solid. It's supposed to be a liquid, and it's supposed to be a gas. And so most people know, for example, that when you change a solid into a liquid, we call that melting commonly. But scientists call this fusion, or chemists call this fusion, right? So fusion would be the melting of something, whether it was a hunk of copper or ice or whatever you want. And then the reverse of this, right, would be freezing. Would be freezing or crystallization. If you look at the difference between liquid and gas, right, if you turn a liquid into a gas, we would just call that boiling, right? You boil a cup of water, for example. But again, the term that chemists use is vaporization, like you evaporate it. Vaporization. And then going from the vapor, the gas, to a liquid, right, would be condensation. And there is no kind of second term. Everyone uses condensation to mean the same thing. Now, you've probably seen all of these in your life, right? You've seen things melt or boil, or you've seen condensation on your glass of ice water, something like that, right? Ones that we don't see all that often are, for example, when you turn a solid into a gas directly, where you don't have a liquid intermediate. You don't have your solid turn into a liquid in between. It goes directly to gas. That's sublimation. So sublimation, the most common thing I think that probably people have seen that sublimes would be like dry ice. Dry ice is a good example of sublimation, right? You have a hunk of dry ice, that big solid, and then it just turns into vapor, right? It never gets wet, which is why it's called dry ice, right? There's no liquid phase there, so it sublimes at our temperatures and pressures. And then the opposite of sublimation is deposition, where a gas goes directly to a solid, again, not going through a liquid, and that would be deposition. Right, where something would deposit, you would deposit something. This is how some snow forms, for example, or some frost forms, is through deposition. Now, as we go through these different phase changes, always, as you go from a solid liquid to gas, so if you go in this direction, you always are going to require heat. Your Q is always positive. It requires energy, right? If you think about your water in a pot on the stove, it doesn't turn into gas just by itself quickly, right? You need to put energy into it so that it starts to boil and turns into gas. You're putting energy in. Ditto for an ice cube, right? You need to get some heat to go into it in order for it to start melting. And then the opposite is true here, right? As you go from gas through liquid through solid, or if you skip it when you do a deposition, the opposite is true, right? Here you release energy. And always your Q is going to be a negative number, right? Your Q is going to be a negative number, and I'll use bullets here instead. I don't want this to look like a negative Q. So always as you go from left to right, you require energy. Things are endothermic. The Qs are positive. As you go from right to left, you are exothermic. You're releasing energy. Your Q is going to be negative, or your delta H values are going to be negative. Right? Remember that again. I wrote Q here, but you could have written delta H also. And so what you're going to see are things like this, right? There's a whole bunch of different values that you're just going to look up. You could calculate them, and we will calculate some of them, but you're often just going to look these up, right? So here's a bunch of phase change equations. So you're going to have things like this is a value you're just going to go look up. This delta H vap stands for the heat of vaporization for something. And it's going to have units like, and I'm just making this up, it's going to have units like 982 joules per mole, for example, right? So it's going to tell you an amount of energy that you need in order to vaporize a mole of stuff. So once you have 1 mole of stuff, here's how much energy you need in order to vaporize it, right? And remember that vaporization is going from a liquid to gas. That's why we need to kind of talk about, right? I had to put this up here. Vaporization is boiling. It's going from liquid to gas. So we need to pay attention to when we're being asked the question, if I want to change something from a solid to a liquid, I'm not going to use this value, right? This is not the energy of going from a solid to a liquid. This is going from a liquid to a gas. And so I wouldn't use that one. I would instead use a heat of fusion. Heat of fusion, right? Because heat of fusion is going to be what you use if you want to go from solid to liquid. And I'm not going to make up another value, but it'll be something else like that. Something, so many kilojoules per mole or per gram or something like that. And then we have here, I should have done different colors. That's okay, I think. It's okay. These colors don't match up there. Sorry about that. Then we have the heat of sublimation, which is going from the solid directly to the gas. And then this is one that we're not going to talk about in this chapter necessarily, not right now, but this would be the heat of solvation. And this would be when you take something, it's either going to be a liquid, so a liquid, I'll put a liquid or solid, and what you're doing is you're dissolving it. So it's going to go aqueous, so you're dissolving it. So solvation, we mean by dissolving something. We're not going to see this yet. We absolutely will talk about this soon. You'll see it in some of the lab work. But these are just different values for when something changes phase, solid, liquid, gas, or even being dissolved. There's a corresponding change in energy. There's a Q here. One thing I also want to mention here, I'll just mention this now. This heat of vaporization, these are the values that you're going to see. You're only going to be able to look up heat of vaporization, heat of fusion, heat of sublimation. You're not really going to be able to find as easily a heat of condensation or a heat of crystallization, a heat of freezing. The backwards values going from right to left are not often in tables of information. But that's okay because we know that the values are equal and opposite. So if I was going for, let me just kind of block this off here. If I wanted to know how much energy it took to go from gas to liquid, that's the opposite of this, right? Liquid to gas, gas to liquid. It's the opposite. That value is going to be the exact same value, 982 joules per mole, as the heat of vaporization. The difference is that it's the opposite. So instead of requiring energy and being a positive number, it's going to release energy and be a negative number. And we're going to see that in some of these examples here that I'm about to do. So don't worry if you can't find a heat of deposition or a heat of freezing or something like that. It's going to be the heat of sublimation opposite, or the heat of fusion but opposite, the negative values. So let me show you what I'm talking about. So let's see we have this question, which is how much energy is needed to boil 568.0 grams of ethanol? And I gave you some values here. I have a heat of vaporization equals that, and a heat of fusion equals that. And so what you're going to want to do when you have these types of questions is say like, okay, the question is telling me that I need to boil something. And I know that boiling is going from a liquid to a gas, or in other words, vaporization. Which means I'm going to use this value here, vaporization. I'm going to ignore this heat of fusion. I don't need the heat of fusion. That's irrelevant for this question. I don't need that, right? Because we're talking about this phase change, not melting something. And so I'm going to use this equation. So I'm going to say the energy needed, the Q, the heat, is going to be G times delta H of vaporization. And one thing you're going to want to keep in mind, like, so this equation will work fine, right? It has grams here, and my heat of vaporization also has grams in it. You're just going to want to make sure that if you're using this equation that has grams in it, that your delta H has grams in it. What you might see instead is you could see, and I'll just put this as an aside here, you could see a delta H VAP that is something like 28.1 joules per mole. And so it's going to be mole here instead. And so instead of having Q equals G times delta H, you're going to have Q equals mole. Sorry, not mole. You don't write out word mole. We're going to write N. N delta H VAP. Where, of course, N is the number of moles. So just be mindful that if you are given a heat of vaporization or fusion or sublimation or whatever per mole, that you're multiplying it by moles, that you don't multiply it by grams. Your units won't cancel. You won't get the right answer. You're trying to mix units here. So what that means is I would have to convert, use a molar mass to convert between grams and moles or vice versa. But this one, my HVAP is in grams. So I'm going to use this equation that has the grams in it, not the moles in it. And then you just plug in the values that you've got here, right? So I'm solving for Q. My number of grams is given to me here. I have 568.0 grams times my HVAP, which is 0.837 kilojoules per gram. That's great. My grams cancel with grams. And so my Q is going to be in kilojoules. So all I have to do is multiply those two numbers together. And if I multiply those two numbers together, I get 475 kilojoules. And that would be my answer. And then I want to double check also that it's still a positive number, right? This is a positive number. This Q is positive, which means it's endothermic. Right, which means it required energy, it absorbed energy, which again should make sense given that we're trying to boil something, right? If we're trying to boil something, you got to put heat into it, you got to put energy into it. So that makes sense. Just make sure that your signs make sense. Now let's do another one. So now in this one, how much energy is needed to freeze 44.2 grams of ethanol? Now we're saying that I need to freeze something, right? Which I know is going from liquid to solid. But if I go back here, right, vaporization is going to be liquid to gas. Fusion is solid to liquid. Sublimation is solid to gas. And this is, solid or liquid or something going to aqueous. So the closest is going to be this, right? My heat of fusion is the closest, right? The only thing is it's opposite. Right, it's opposite. So that means I'm going to go ahead and use the delta H of fusion, right? So if your delta H of fusion is 106 joules per gram, or in other words, when I'm going from solid to liquid, then that means that if I'm going to put my delta H of fusion in here, but flip it, right, going from liquid to solid, which is what this is asking for, it's just going to be negative 106, right? We just put a negative sign in there because it's going to be the opposite. It's going the opposite direction. And I flipped it because I want liquid to solid, just like we are when we freeze, right? Liquid to solid. It's fusion, but opposite, so we use the negative sign. And I'm going to use the same equation here, right? Again, these are in joules per gram. So I'm going to use gram. So Q equals G delta H of fusion. And I'm going to be mindful now that my Q equals, okay, my grams is 44.2. My delta H of fusion, I'm not going to put 106, I'm going to put negative 106 because I'm doing the opposite of fusion. Joules per gram. My grams cancel out. And then my Q is going to equal, let's see, negative 4685.2 is what my calculator says, but right, really that's going to be negative 4.69 times 10 to the 3 for my sig figs. And again, here my Q is negative, which means it's exothermic. Which again should make sense with what I was saying a couple slides ago, which is anytime we go from gas to liquid to solid, those are going to be negative values. Those always release energy. They release energy. I know it seems weird that freezing releases energy, but it does. You're forming actually new bonds between the things that you're freezing, in this case ethanol, and that releases energy. So that's kind of how we approach these, right? You just got to make sure that you got to pick which one of these three most resembles your phase change. That might be opposite. If they're opposite, you just flip the sign, and now you've got the heat of crystallization. Basically, is what you've got, the heat of freezing. So I want you to do one now. Okay, folks. So for this one, I want you to read through this and then take a moment and try this yourself. Right. So how much energy is needed to melt 2.09 times 10 to the 5 grams of water? And I give you that the delta H of vaporization is 40.67 kilojoules per mole, and the heat of fusion is 6.01 kilojoules per mole. Now, again, I want you to take a crack at it yourself, but I do want to point out, right, just we're starting off with grams, and all of these are in moles. So that should give you a hint to your first step. You're very smart people. I think you can handle it. So go ahead and pause and see what you can do with this one. Okay, so if I take a look at this, right, first, if I want to use these heat of vaporizations, right, first of all, let me back up. We know that my Q in this case is going to be the number of moles times my heat of whatever, either vaporization or fusion. If I take a look at the question, it says how much energy is needed to melt. That's pretty straightforward, right? We know that melting is going from solid to liquid, which is fusion. So I am going to use this value right here, right? So it's going to be delta H of fusion. But I need to figure out my N here, right, which is number of moles, right? I need moles if I'm going to use this number. How am I going to figure out the number of moles? Well, I'm starting off with the number of grams, right? So I have the 2.09 times 10 to the 5th grams of water. And I know if I just look up the molar mass of water, if I just add up 2 hydrogens and oxygen or just look it up on Google, that there's 18.015 grams for every mole. And that's going to give me 1.16 times 10 to the 4th moles. All right. So that's going to be the number of moles that I'm able to use in my Q equation right here, right? How much heat is being transferred. So now that I know how many moles there are, I can go ahead and I can use my Q equation, right? So my heat equals the number of moles times the heat of fusion. I now know that the number of moles is 1.16 times 10 to the 4. And I know that my heat of fusion is 6.01 kilojoules per mole, because that was given to me. And if you solve for that, you just get that your heat equals 6.97 times 10 to the 4 kilojoules. And that's it. So apparently this requires that much energy. And again, you want to think about the value, right? This is a positive value. I didn't get a negative value here. And in order to melt water, that water needs to absorb that energy. So that should be a positive value, if that makes sense. So you always want to double check yourself. So I hope that gives you a little bit better idea about how to calculate the energy changes for changes of phases. Study up, watch the next videos, and good luck.